I want to begin this video by using two animations from the Wolfram Alpha demonstrations website. The first one has to do with approximating the area under a curve using a Reimann sum. And here I have a curve, and I want to approximate the area from x equals 0 over to x equals 5. And I can do that with four rectangles using a right endpoint as I have shown here. And you'll remember that the concept of finding the actual area is to increase the number of rectangles, n, make n go to infinity, which basically means that our width of each rectangle, delta x, approaches 0. And if we do that, the more rectangles we have, that area will approach the actual area under the curve between 0 and 5. And so we can think of the area under a curve f of x between x equals a to x equals b as being the sum of an infinite number of infinitely thin rectangles, delta x approaching 0, from x equals a and stacking them infinitely thin up to x equals b. The sum of all of those will be the actual area under the curve. Now what I want to do is look at how this idea can be applied when we're dealing with polar curves. The difference, of course, with polar graphs and equations is that our equation is theta with respect to r. So various angles theta produce different values of r, which creates the points on our curve. In this case, I have a curve with 3 petals on it. And so my initial angle, you can see, which is represented in blue here, is 0 radians, and what I'm going to do is I'm going to increase the angle, which as I do that is going to sweep out an area between the curve. And I'm going to go right up to that point there, right for the area of that first petal has been completed, and that angle we could actually calculate to be pi over 3. And so we want to calculate the area in red. Now you'll notice that we haven't broken it into rectangles. What we've done instead is, as the sweeping was happening, we were breaking our region into n sectors. Okay, so you can see all of the different sectors, which is like a piece of a circle. And if we take our sectors and make them infinitely thin, which in this case would mean to make the change in the angle infinitely small, that would allow us to find the actual area of a petal. And then we could continue on. We could either multiply by 3 to get all 3 petals because they're symmetric, or we could work all the way around to an ending angle there. But the concept I want you to pick up on right now is that if you have a polar curve, r as a function of theta, then we can conceptualize the area between angle alpha and angle beta. So the area we're trying to calculate is this section here. Instead of breaking that into rectangles, we're breaking it into sectors because the breaking up is based on the moving of the angle. So there's, let's call that's curvy there. Let's call that the kth sector. Okay, let's just show it here. And what I'm going to want to find is the area of this one sector. Now you need to recall from some time ago we talked about finding the area of a sector, and you can get it by this formula, 1/2 radius squared theta, where theta is in radians. And so in terms of this kth sector, our radius would be this as a function of theta, and our angle is the change in this angle, which we can represent as change in theta. You see the comparison to when we did rectangles, where we took a change in x to represent our width of rectangles. The change in theta is going to represent the change in the angle. And so what we can do with that is that the area of our kth sector will be, applying our formula, 1/2 r squared times our angle, which is the change in theta. We can then get the sum of n sectors by summing up n sectors, k goes from 1 to n, of each sector, and we can then find the actual area of the region between angle alpha and angle beta by taking the limit as the number of sectors approaches infinity, which is equivalent to the change in the angle approaching 0 of our sum of n sectors. And this statement we know can be expressed as a definite integral. The sum, as the angle goes from alpha to beta, the 1/2 can pull out front since it's a constant, of r as a function of theta squared, and delta theta becomes d theta as our limit takes hold. And this is our formula for finding the area bounded by the curve in polar form with angle going from alpha to beta. So let's apply this to find the area enclosed by this polar equation. So first of all, I need to come up with just a little bit of a picture of this. I could use my calculator, but let's just see what we can figure out on our own. We're told it's a cardioid, this graph, but let's just see how this works. So if my angle is 0, it's always a good place to start. Cosine of 0 is 1. 1 minus 1 is 0. So that polar coordinate, when graphed, will be right there. Another convenient value to pick for theta would be pi over 2, because the cosine of pi over 2 is 0, and 1 minus 0 is 1. And so at an angle of pi over 2, my radius is 1, so I have a point there. Let's go to pi. Cosine of pi is negative 1. 1 minus negative 1 would be 2. So at an angle of pi, I'd have a radius of 2. The point would be there. 3 pi over 2. Cosine of 3 pi over 2 is 0. 1 minus 0 is 1. So at an angle of 3 pi over 2, I'm 1 unit out, radius, which is there. And then at 2 pi, I'm going to be back to the same value I got when I plugged in 0, which is 0. And if I think of values between 0 and pi for the angle, I can see the radius is going to grow from 0 up to 2, and then decrease from that point 2 back to 0 once we get back to an angle of 2 pi. So the graph's going to look something like this. Here's my electronic visualization of it. So if I start at an angle of 0 and I start swooping out, I can see my sectors being created, n sectors going all the way around. What I'm trying to do to begin with is figure out my starting angle and my ending angle that will encompass the entire area that I'm asked to find. So indeed, in this case, if I go from 0 radians to 2 pi radians, I will have swooped out the entire area with n sectors. And so I can take my limit, which is doing my definite integral. So my area will be my definite integral from the starting angle to the ending angle with respect to theta, and plugging in my formula, 1/2 radius squared, and the radius is my equation, 1 minus cosine theta squared. And I can pop that into the calculator to get an answer. You can check that on your own. If you do that, you get 4.712. And yes, we can extend this idea to find the area between polar curves. Let's suppose I want to find the region enclosed by R2 and R1 from theta equals alpha to theta equals beta. In other words, I want this enclosed region. And so what I can do is take the area between alpha and beta swept out by R2. It's the one furthest out. There's an individual sector right there. Subtract the sector up to R1. to get this little piece in here. The outer sectors minus the inner sectors to give me just the enclosed region in green. And that statement can be expressed as so. Alright, let's find the area inside the polar curve given and outside the polar curve r equals 3. Alright, so let's just see if we can sketch these curves on our own without any help from the calculator. Some of you might immediately recognize this as a circle with a radius of 3. If you don't, you could probably reason it out just by taking a few simple points. If the angle is 0, sine of 0 is 0, and so my radius is 0, so I'm starting here. At pi over 2, sine of pi over 2 is 1 times 6 would be 6. So that would be 6 units out here, 6. And for pi, we would actually be back to 0. And if you take values in between, you'll see that it's a circle like so. But we have this other curve, r equals 3, which we should recognize as a circle with a radius of 3. And so we want the area inside the black curve but outside the red curve, which will be this section in here. And so what I need to do is I need to look at where my starting angle will be. I'm going to want my starting angle to be right there. Don't know what that is. And I'm going to swoop from that green, moving counterclockwise over to here. Angle beta. Now, the key to getting the angle is to note that the points of intersection of the two graphs. So I need to find the point of intersection of 6 sine theta and 3, which in other words means I have to make them equal to each other. So sine theta is a half, and if I inverse sine that, I'm going to get angles of pi over 6. And in quadrant 2, I can visually see it's in quadrant 2, 5 pi over 6. So, to get my area, it's going to be 1/2 the integral of the lower angle, pi over 6, the smaller angle, to the larger. You can think of the swooping out, the angle moving from pi over 6 to 5 pi over 6 with respect to theta. The outer minus the inner radius. So the outer radius I can see is the 6 sine theta squared and the inner 3 squared. And there's my expression. Alright, we have everything set up with a calculator. Let's just check out our graph first. There's our circle up top and our circle centered at 0, 0. And we want to enter this expression. So on a blank screen, 0.5, our integral, and pi over 6 to 5 pi over 6. R2 of this function, which I have entered as R1 on mine. So over to variables, and I'm using polar, number 3, R1 squared minus variables polar R2 squared with respect to theta, and that's coming out to 17.219 is the area in blue. Approximately 17.219.